Okay, let us know when you're ready.
We're ready when you are.
All right, fantastic. So welcome to week one. Am I still in frame? Could you just, because the other week I was recording and I was like way out of frame. All right, fantastic. Welcome to BinarX program week one. So payloads and questions. So you had the overview last week of the BinarX student payload development program. If you have questions, we'll have time at the end, we can clarify. But today we're just going to talk about why we go to space, what sort of things you can detect in space using your payload, and what science questions you might want to answer. Don't worry, it's all kind of very high level brainstorming at this stage. We'll do a little bit of brainstorming, what interests you, what you want to investigate, and then from there we decide what kind of payload we're going to develop. So it's more just a concept today. So the BinarX mission is the 2-year mission to enable high school students to design, build, and test their own payloads on future Binar CubeSats. And while you're waiting, because you didn't get a chance to look at this last week, because I wasn't here, that is the display model of Binar 1, and this is a 3D printed model of Binar 234, which is flying hopefully in August. And that's a little bit different. It has deployable solar panels and it has a removable payload bay. This is where your payloads will go, and that's what gets launched onto orbit. So I'll pass those around, you can have a look. Oh, and for the benefit of Balcata, you saw this last week. You remember the two Binars? So we had those as well. No, that's the actual size. That is the size. It's a 10 by 10 by 10 centimeter. They weigh about 1.3 kilograms. Are you doing all right there, Balcata Senior High School? Thumbs up, excellent. All right, we will proceed. So what is a payload? A payload in a CubeSat is all the equipment and tools packaged into the CubeSat to actually do the job. So it's an instrument, effectively. So whereas the CubeSat bus is the satellite that goes up there, it's what's powering your payload, and your payload is gathering all the data that you want to gather and sending that, and you're going to ask for it over the ground station and get it sent back down to Earth. So the simplest payload would be a single sensor that would take a measurement from the space environment or Earth observation, which is a very common thing, whether they're looking with infrared or optical sensors to try and measure different things about the Earth. That would be the simplest thing. So it still allows a variety of experiments to go into space, even though that is a very simple payload. But we'll talk more about sensors as we go through. But you can use radiation sensors, infrared sensors, light sensors, temperature, thermopiles. It's very, very cool. There's lots of different things you can do. So things you might want to do in terms of payloads that have gone before. You could replicate early space experiments. So you could use a radiation sensor to try and detect the Van Allen belt. So those are belts of radiation that go around the Earth. You can Google that and find a bit more. You can use what's called a magnetometer, so basically a magnetometer. You can measure the Earth's magnetic fields, and we actually use that on our CubeSats to help us turn our CubeSat. And I'll explain more about that later. Oh, sorry, was there a question, Mr. Briggs?
No, we're all good.
Yeah.
I'm just having some technical difficulties.
Okay, that's all right. So for Binar 234, we're actually testing some radiation shielding for CSIRO. So our payload in that case is a radiation sensor that is going to behave in a certain way based on how much radiation it gets. But you could also observe the Earth. You could use a UV sensor to study the ozone layer because of how much ozone is reflected. You could look at light sensors to measure measure albedo or the greenhouse effect. You can also look at coral bleaching. I think one of your teams here is looking at coral bleaching. Or you could just detect cosmic or stellar phenomenon to study astronomy. For example, using a radiation detector to study solar flares and the solar wind, or a particle detector to detect cosmic rays from supernova. So you can do all kinds of things. You can even, I think it would be great to do something artistic where you measure something in space and then you can make something called a sonograph, and you can actually take the data and turn it into sound or turn it into art. There's a lot of really different ways you could do that. And why would you do that? I think science is really important, but I think getting people on board and sort of getting them to care about space and engaging them in different ways is important as well, and really valid. So how to choose? Oh, sorry, I'm standing right in front of the PowerPoint. You can't even see it. So you could ask questions about, and so at this stage, don't worry about what sensors you're going to use, about how you're going to do it technically. Just what question do you want to ask? So Dr. Rita Jones did this lovely diagram, and she's a planetary observation expert or specialist at Curtin University. She said, how would you choose your question? Well, if you imagine you're sitting by a big glass window in a spaceship and you're looking at Earth, what would your questions be about our home planet or about the environment around you? So you could have questions about climate change and environmental impact, which is obviously huge right now, and weather patterns and natural disasters. So I don't know if you can think of natural disasters were quite common here in Australia. What sort of natural disasters do we have quite frequently?
In Australia?
In Australia, kind of.
Natural disasters.
There's a few.
Every summer. What's going on up in the north of Australia almost every summer?
Droughts?
Yeah, but like disasters, cyclones,
Yeah.
bushfires.
Fires. And then on the other side of Australia, what do we get over there? They get lots of, and actually we had it up in the Kimberley as well last year. Something else we might get would be the opposite of a bushfire.
What happens when it rains too much?
Tsunami?
Well, yes.
That's more of an earthquake.
Yeah.
Earthquake. Flood. So you can measure different things remotely from we'll be in low Earth orbit, so it'll be about 400 kilometers away from the Earth, going around the Earth in the satellite, and that's where your payload will be, hopefully blinking away and measuring whatever it is you want to measure about the Earth, and sending that data down to you. So. Urbanization and population growth. So in terms of urbanization, there's something called the heat island effect. So the more concrete you have, or the less tree cover you have, and Perth has one of the least amount of tree cover for cities in the West. And what happens then is that when the sun hits the ground, it heats up, it stays hot, and we have all kinds of nasty weather during the summer when it's hot. So it's important to study that, and that helps architects and city designers maybe make better decisions about planning and where they need to plant trees and open spaces and parks, or water resources. What's happening with dams and catchment levels, what's happening with the ocean, what's happening with salinity or contaminants in the rivers. There are so many different questions you can answer, but I want you guys to have a think about what problem you think you could observe from space and get information about, or just what interests you. If you just want to take a picture of space, you can, but you've got to keep in mind our payloads or our CubeSats. We have a very, very small amount of data, so it's not like we're streaming 4K Netflix down from the satellite. You've got probably a really small, I don't know if you've ever seen the really old cell phones, back in the day. Not great images, but we want more data than images, but you're still, images from space are still amazing. So that is something you can incorporate into your payload. So today we don't need to think too much about the details, but start thinking about what you want to observe from space, in space, and what question you want to answer. So there is a link here, and you can follow that. That's actually a research journal to very, very technical stuff, but talks about other CubeSat payloads. That's maybe for your teachers to have a look at. But you brainstorm your own payloads, and your process when you're brainstorming and developing your payload is sort of start with your science question or your philosophical question, your art creative question. I want to answer that question. What is it going to take to get the data to answer that question? So the measurement requirements. And then you're going to have physics, which is the space environment. I mean, there are constraints of, from a technology perspective, how much space we have, how much data allowance we have, how much power we have. And then obviously the space environment, it's a vacuum, it's cold, it goes hot and cold cycles very, very intensely. But that's later in the game, and then you'll actually design the instrument and then integrate it with the spacecraft. But that's later on down the track, so just keep thinking about what question do I want to ask, what problem do I want to solve. So the payloads, we won't be controlling them all the time from the ground. You've got to make them sort of self-contained. They'll only be on for a little bit of the time. It's not on all the time because we don't have a lot of power. We use solar panels to power our CubeSats and charge the batteries. You'll have an experiment where you say, okay, I'm going to turn myself on. I'm going to take some measurements using my payload. I'm going to send the data, and then I'm going to turn off for a little bit. So that's something that you've got to think about. And then we only get the satellite over on a certain orbit. So we actually launch off the International Space Station right now. That's what we're launching off of in August. So the orbital path, and we'll talk a bit more about this, the orbital path currently for our satellites is expected to be approximately the same as the International Space Station. And I'll show you in a minute a website. You can actually go and see where the International Space Station is going to be at any given time. And that frequency of passing of the International Space Station is about how frequently you would expect your satellite to kind of come over. And that's when we can get your data. We can't just send it at any time. We've got to wait for it to be overhead, and then we aim our antenna, and we get your data, and we give you your data, and then you take it and you do what you need to do with it. So we did, I talked about this in the introductory session, you know, the school holiday program. Did Miss George go over that with you? Yeah, we ran the program, but we ran it in model rockets instead of in cube satellites. But this is effectively kind of what the development looks like, and that's what the students who are already participating, they're doing those electronics boxes. So we started with a bit of prototyping, but then we actually made this electronics payload. And I've brought this for you students today as well, because I know, Balcata, you had a chance to look at the payload development kit last week, did you not?
We did, yes.
Excellent. So I've brought this over so that eventually this is what your payload will be built on. So you'll design a circuit and sensors, and it'll get built on here, and you'll do some software. It's not tomorrow. It's down the track, so don't worry. You'll learn a little bit at a time and a little bit at a time, but that's what it's going to go on, and then that goes into this payload, and I'm just going to go in front of the camera so my MLC and other schools can observe. That goes in there. This way to space, we've got a little handy arrow showing us which way to space. We pop that in there. That goes in our CubeSat and will be bolted in much better than what I'm doing now, and then that goes out onto orbit. So if it's an optical sensor or something that requires to be pointed, you need to worry about which way it's going, and you also have to, you know, make sure that happens, but not all sensors need to be directed at things. You know, radiation sensor will just detect particles in the air. So you can pass that around. I won't get into this today. This is the payload development kit for later on down the track, but you actually will get to test your payloads. That's sort of a pretend satellite flight computer that operates the same way as the computer on there, but that's all done with software. So it's quite fun. And then, yeah, at the end of this year, you'll hopefully have a prototype that you can come. Your students came on, and that's John Curtin College of the Arts. They took their prototype payload, which wasn't space ready, but conceptually was at a certain point, and we put it in a vacuum chamber and subjected it, because a vacuum is in space, there's no air, it's freezing, it gets really hot. So we basically put liquid nitrogen in, subject it to all those sorts of tests as well, so you'll get to test out your payload before it goes to space. So yeah, that's a better rendering of that in there. So your payload in here goes in there and goes to space. So that's it. That's what you're passing around now. So that's quite cool. Those clip together, and that's a little bit better of an image of how that's going to sit in there. So we'll fit up to 4 payloads in a satellite. We're hoping to launch 3 in 2026. We don't have the dates yet or the orbital path, but when you're thinking about your payload, you might want to say, you're not going to measure the whole world. You know, we've got, I'll show you an image of one that is currently being worked on. Oh, I must not have updated it. But currently our team are working on measuring moisture content in Western Australian forests to help the DFES manage their, be more strategic about how they manage forests. And then obviously prevent, the low moisture content in those forests. They will prioritize those for management, and that's done done using an infrared sensor. So yeah, there's lots of different kinds, but the idea is today just have a think about what you want to ask, about what questions and what problems exist in your community. Do a bit of research into those specific journals that I sent through for the teachers to start getting an idea about what other people do, but it doesn't have to be complicated. It can be something simple if you just want to go through the process of designing a sensor and actually getting that data from space and actually having something out in outer space. That's very cool as well. And there's lots of fun stuff we can do in the meantime. We did a high altitude balloon launch 3 weeks ago, and we went up 29 kilometers, and we actually got a photo showing the curvature of the Earth from the stratosphere. So we were almost in outer space, but not quite. So there's lots of fun stuff we can do while you're developing your payloads to actually test your hardware and your software and your concepts before we launch it on the CubeSats. And that's quite fun, because you go out to the country and you fill a giant helium balloon. I don't know if you've seen our Instagram. If you hop onto our Instagram, there's some very, very funny sped up videos of us trying to wrangle a giant helium balloon. So I'll just hop onto here. So the Spot the Space Station, this is, I don't know if you can see that. Yes, you can. So that's that's spotthestation.nasa.gov. You can go in and put in your location. There's actually an app as well. And if you want to sort of get an idea of where you might be passing overhead with our satellites, once your payloads are there, you can see how often. And it's actually fun. I think it's going over tonight, and you can have a look in the space. The International Space Station is very, very easy to spot in the night sky because it's very bright. It's always in the same spot. An interesting thing is as well, I'm not sure if you can actually talk to it, but another website that we're going to talk about is SatNogs. So that is another part of the program where you make a ground station, and you can do this with very simple parts. And we do have kits that we make available. You can go and you can actually get data from satellites that are already on orbit. And that is an open source project. And a challenge for the BinarX program is for students to also build their own ground stations and communicate with their satellites or other satellites using their own student-built ground station kits. So that is a lot of fun. So that's just satnogs.org. That's all open source. Ignore. And then so for today, maybe just have a think, but you can also, Google, have a look, if you Google past CubeSat missions, this one's kind of my little personal pet favorite, which was done in 2010. It was called ArtSat, and it was a Japanese university, and they did a full art interpretive cube satellite called Invader, and they just read, got data from the universe and then interpreted it in different ways, and I don't know. So it wasn't as much science, but there was, there's always going to be science associated with it because, it is demonstrating technology. So yeah, thank you for that. Do you guys have any questions, any ideas about what you might want to do? I brought Post-it notes, Balcata Senior High School, but I'm afraid I don't have any for you today. That fun little, yes, go ahead.
When are we gonna start designing it? Like, when are we gonna start designing the CubeSat?
Well, you're not designing the CubeSat itself. You are going to be designing the payload that goes into the cube satellite.
Yeah.
Well, oh, sorry, go ahead.
Also, is this gonna go on during the holidays?
It won't go on the school holidays. We'll give you a break. I mean, you can go with your teachers. I won't come out during the school holidays. We did run a school holiday program over over the summer break, but I'm not sure if we'll do another one. But we're mostly running it in term. But in terms of starting to design, we're already starting to design because the first stage in any design process is to identify the problem and to think about it and think of all the ideas. So when you're brainstorming, have you done a lot of brainstorming?
Yes.
Yeah, so remember there's no bad ideas. You get them all out and then you start to identify which ones are the best ones and you can group them together. That's why I like to use Post-it notes. And you can, so maybe brainstorm about, what's in space or what questions you want to ask or what environmental problems exist or what, even philosophical questions you want to answer. What is sound, what are the sounds of space? If I measure this data, how would that sound? It's totally up to you, but we're starting today. Okay. But in terms of the soldering and stuff, we don't do that for a little bit later, but you can definitely get stuck into it if you like. Yeah, is that the fun part for you? Yeah, awesome. Well, you get into those Introduction to Electronics kits, and you can ask Mr. Briggs to get some of the rocket payload development kits from us as well, and you can start playing around with it on the ground. You don't have to wait to go to space to design a payload. You can start doing the rocket program, and that is a lot of fun as well. And then make it for space.
Yep, absolutely.
Awesome. Well, shall I leave you to continue the session with your students, Mr. Briggs?
Sorry, say again?
Shall I log out and leave you to continue the session with your students? Because I'm going to sit and work with Joseph Banks. So thank you. So you'll be zooming in with Joseph Banks when I come and visit them at their in-person session. Or sorry, when I come and visit you, they will join you virtually via Teams. So that's awesome. So that means you guys will be sort of getting to touch base with me personally every other week instead of every 4 weeks, which I think is really great. I prefer to be in contact rather than just virtual talking head Meg on a screen. I'm interactive.
Not a problem. We'll handle things arranged.
Awesome.
And, we'll see.
Thank you so much. And any questions, just email on through.
Excellent. Will do.
Thanks, Mr. Briggs. You have a great day. Bye, everyone.
See ya.
Thank you. So I'm just going to turn off. Whoop. This one, hopefully. Oh, it died on me, so I haven't been recording all that well, but that's all right.